In the name of Almighty God, I'm Mahsa Sankasha, and today I want to talk about microscopic diffusion of partially ionized metals in the Sun and metal-poor stars. Now I want to go through the next chapter, which is partially ionized elements in Berger's equation and the method to calculate diffusion constants, as described by Toll and his colleagues in 1994. Denoted TBL hereafter is followed, where the basic concepts and quantities can be found. The aim is to improve this method in particular by including partially ionized atoms in addition, a possible non-ideal electron gas and the contribution of radiation pressure to the hydrostatic equilibrium equation are taken into account, the effects of which are neither considered by TBL. Besides, in this section, nuclear burning is neglected. It can simply be added afterwards. The next section is 2.1 Basic equations. An oral natural plasma consisting of S species is assumed, where species is defined by an element in one particular ionization stage. Electrons are supposed to be species number S and are usually not mentioned explicitly. Becker's equation for mass conservation can then be written as these equations in 11. But here we have it. The first equations, the partial derivatives of ns based on the time is equal to minus 1 divided by r to the power of 2. The partial derivation divided by r to the power of 2 omega and n, when r is the radial distance from the center and ns is the number density of ion s. The diffusion velocity omega s has to be determined by solving the momentum and energy conservation equation based on the equation 18.1 and 18.2 of Berger's in 1969, neglecting magnetic fields. The DAPS based on the dr plus rho s divided by rho DAP gas divided by dr minus PAS E is equal to F1 m omega RH. And the next equation 3, 5 divided by 2 PS multiplied by dA and NSE divided by dr is equal to F2 m omega H, where PS, rho s, NS, MS, and rho es is equal to NSQS, are the partial pressure, mass density, and charge density respectively. For ion S, with Ms being its mass and Qs its charge, is the electric field strength. The vector m and omega contain the mass and diffusion velocity for each ion S. For detailed definition of the friction coefficient, tensor call the residual heat flow vector RH and the function Fa1 and Fa2. The region is referred to TBL. The total pressure P is composed of radiation, P radiation, and gas pressure, P gas. Thus, we have a P is equal to P radiation plus P gas is equal to P radiation plus sigma Ps is equal to sigma 1 divided by beta Ps, where the standard definition beta is equal to P gas divided by P has been employed since the departure from local charge neutrality is very small. CFTBL rho E is close to zero, and thus the usual hydrostatic equilibrium equation would be dP divided by dr is equal to minus g rho, can be used with g being the gravitational acceleration. Hence, equation 2 becomes dPs divided by dr plus beta g rho s minus rho s divided by rho the derivative beta based on the r minus rho es e is equal to f of 1 m omega rh. By two additional constraints, current neutrality would be based on the equation sigma Qs ns omega s is equal to 0 and local mass conservation sigma ms ns omega s is equal to 0. Equation 3 and 5 are completed to form a closed set of the 2s plus 2 equations for the unknown quantities omega, h, g, and e. For a large number of species with varying abundances, these equations are preferentially solved numerically for this purpose. They are formulated to be more suited for stellar evolution calculations. The partial pressure Ps for atom S is given by the ideal gas equation Ps is equal to Ns squared Bt. The electron pressure in the stellar envelopes is well described by this formula too. However, in the deep radiative regions of low-mass stars, and in particular in white dwarfs, the electron gases degenerate. Therefore, an effective electron density is introduced. Ne is equal to PaE divided by KBT, such that the total pressure can be written as this equation: P is equal to 1 divided by beta sigma Ns square B and T. Where Ns is equal to Ne, furthermore, the concentration Cs is defined by Cs is equal to Ns divided by Ne. Analogously to TBL, which C is equal to sigma Cs, one can now write Ps divided by beta psi P is equal to Ps divided by sigma Ps is equal to Ns divided by sigma Ns and is equal to Cs divided by C, and hence the first term of equation 5 becomes dPs based on the dr is equal to dCs divided by C beta P divided by dr is equal to Cs divided by C or beta P multiplied by dln beta P divided by dr plus dln Cs divided by C divided by dr. Taking into consideration that in TBL the pressure P has been defined to be solely the gas pressure, this term seems to agree with TBL. However, here Cs has been defined via equation 10 instead of TBL's equation 22. Cs is equal to Ns divided by Ne, which accounts for possible degeneracy of the electron gas, demanding charge neutrality. Sigma s is not equal to E. Qs Nas is equal to minus QE Ne. One gets rid of the dependence on one species, for example, hydrogen helium plus plus. Thus, we have a zeta helium plus Ca helium plus plus is equal to Cae minus sigma L boundary S is not equal to helium plus plus and electron. Zeta S is the ionization stage of ion S. Zeta S is equal to 0 for neutral atoms, and Ca is equal to Ne divided by M per Ne. Similarly, the LHS of equation 3 becomes 5 divided by 2 Ps dlnT divided by dr is equal to 5 divided by 2 Cs divided by C beta P dlnT divided by dr, setting equation 8 till 15 into equations 3 to 7. One finds after some algebraic manipulations that the diffusion velocity can be written in general as C appendix R. Omega s is equal to T to the power of 5 divided by 2 divided by rho zeta s. Figure 1 illustrates the contributions of the six terms in equation 17 to the diffusion velocity of hydrogen in a 1.1 m star near the 2, with initial Fermi based on the hydrogen is equal to minus 1.3 zeta s to the power of p solid line and zeta s to the power of t short dash. and zeta to the power of c dash dot is equal to 10 multiplied by zeta s to the power of zeta dash dot dotted, then multiplied by zeta s to the power e dot and zeta s to the power of zeta line dash. The thin solid line represents the zeta s to the power of c plus zeta s to the power of zeta. And the B section, we have the hydrogen mass fraction in this model, where zeta is equal to is to the power of p d ln p divided by dr plus is to the power of t d ln t divided by dr plus sigma. The lower boundary t is not equal to e helium plus plus its to the power of cdln cat divided by dr plus is to the power of beta dln beta divided by dr plus ies to the power of c dln c divided by dr plus sigma. Lower boundary t is not equal to e its to the power of zeta dln satiety divided by the diffusion coefficient r to the power of p, r to the power of t, r to the power of c, and r to the power of beta, and r to the power of zeta are obtained by the solution of equation 3 up to the 7. For convenience, the six terms of equation 17 are denoted zeta s to the power of p, zeta s to the power of t, zeta s to the power of c, zeta s to the power of beta, zeta s to the power of e and zeta to the power zeta respectively compared to the analogous equation in TBL equation 43. Additional terms appear here. They should not be considered as new types of diffusion, but rather as correction to pressure terms and concentration diffusion terms 5 and 6. In particular, the four terms in equation 17 suggests Betsa corrects for the appearance of the radiation pressure in the hydrostatic equilibrium equation. The fifth term suggests the power of E takes into account that for the generate electrons, the ideal linear relation between pressure and density is not valid anymore based on the equation 14. Thus, this term is only important when a stroke gradient in the electron degeneracy appear, for example, white dwarfs. In figure 1, A, the contribution of each of the six terms in the equation 17 to the diffusion velocity omega of H in a 1.1 m star near the turn off TO or sham pressure zeta s to the power of P and temperature diffusion zeta s to the power of T are clearly dominating in most parts of the stellar interior near the center where already most of the hydrogen has been consumed. Concentration diffusion zeta s to the power of c becomes important. The contribution of zeta s to the power of beta remains very small throughout the star, while zeta s to the power of e increases towards the center, where the electron degeneracy is gradually increasing. So thank you so much for watching my tutorial video until the end. Today is the 21st of August 2026. Time is near 10 o'clock in the morning. If there is any simulation for this situation, you can find from github.com/masterscript, github.com/consciousscript, and github.com/staffroyalscript.